Hello everyone, myself Dr. Harisankar Singh. In the previous video, we have discussed about the Maxwell first equation, and in this video, I will give brief description of the Maxwell second equation, that is Gauss law of magnetostatics. Earlier, we have seen this generalized form of Maxwell's equation. Now we have to discuss the second Maxwell equation. You can see in this table, Gauss law of magnetostatic field gives the Maxwell's second equation. As we know, Gauss law of magnetic fields is similar in the form but different in the content from the Gauss law of electric fields. For both the electric and magnetic fields, the integral form of the Gauss law involves the flux of the fields over a closed surface, and the differential form specifies the divergence of fields at a point. The key difference in the electric field and the magnetic field version of the Gauss law arises because opposite electric charges, you can call positive or negative, may be isolated from one another and exist isolately, while in the opposite of magnetic poles, you can call north pole or south pole, always occurs in a pair. We have all discussed in the previous videos of the magnetostatics and electrostatics. So we can see the apparent lack of isolated magnetic poles in nature has a profound impact on the behavior of magnetic flux B and on the divergence of magnetic fields. So you can see this in the table. Remark that never exist isolated magnetic poles. So we will discuss in more details about the Gauss law of magnetostatics in this video. Now let us see this equation in detailed manner. Gauss law for magnetostatics in the integral form is written as closed surface integral B dot n cap dA is equal to 0. The left side of this equation is a mathematical description of the flux of a vector field through a closed surface S. In this case, Gauss law refers to magnetic flux B as the number of magnetic field line passing through a closed surface S, and the right hand side is identically 0. Therefore, we can say that the total magnetic flux through a closed surface must be 0. And why it is 0, we will discuss later on. Here is the expanded view of the equation where each symbol have different meanings. The closed integral is used, that is used for the closed surface. B is the magnetic field defined in the Tesla, and it is vector quantity, so represented by with arrowhead. And dot product tells you to find the part of magnetic flux B parallel to n, that is the unit vector, and it is normal to the surface, where n cap is the unit vector normal to the surface. And this shows that if surface is closed, magnetic field line will always be perpendicular to that surface, and dA is the incremental surface area and it is defined in meter square, and right side is 0. Gauss law of magnetostatics arises directly from the lack of isolated magnetic poles in the nature. Since every magnetic north pole is existed with a magnetic south pole, thus the right hand side of the Gauss law for magnetic fields is always 0. Now let us understand each and every part of the Gauss law of magnetostatics, that is Maxwell's second equation. Just as the electric fields may be defined by considering the electric force on a small test charge, similarly the magnetic fields may be defined using the magnetic force experienced by a moving charged particle. We have already discussed in the magnetostatics video that charged particles experience magnetic force only if they are in motion with respect to the magnetic fields. As shown by the Lorentz equation, the magnetic force is defined as F is equal to Q vector u cross vector b, where Fb vector is the magnetic force and q is the particle charge. Vector u is the particle's velocity with respect to magnetic field v, and vector v is the magnetic field, and it has unit Tesla. So from this equation we can say that the magnetic field is directly proportional to the magnetic force, and also we can say that the magnetic field may be defined through the force experienced by a small test charge. The speed and direction of the test charge, that is north or south poles, must be taken into the consideration. The magnetic fields may be represented using field lines whose density in a plane perpendicular to the line direction is proportional to the strength of the field. These figures shown here are examples of several magnetic fields relevant to the application of Gauss law. Some rules are given here that will help in the visualization of sketching of magnetic fields produced by the current. So some conclusion is that magnetic field lines do not originate or terminate on the charge. They always form the closed loops. The magnetic field lines that appear to originate on the north pole and terminate on the south pole of a magnet are actually continuous loop. Within the magnet, the field lines run between the poles, and the net magnetic fields at any point is vector sum of all magnetic fields present at that point. Magnetic field lines never cross to each other. You can see here infinite straight wire carrying current I, circular loop of radius R carrying current I, torus with n turns and radius R carrying current I, bar magnet solenoid with n turns and having length L given current I. And this is basically all example where number of magnetic fields line are passes through different enclosed surfaces. No matter what shape of the surface you choose, you will always find that the number of field lines entering the volume enclosed by the surface is exactly equal to the number of field lines leaving that volume. This means the net magnetic flux through any closed surface must always be zero. But unlike electric field lines, magnetic field lines do not originate and terminate on its charges. Instead, they circulate back on themselves, forming a continuous loop. If one portion of a loop passes through a closed surface, the another portion of that same loop must passes through the surface in the opposite direction. Thus, the outward and inward magnetic flux must be equal and opposite through any closed surface. Look at this figure. Here closer view of the field produced by a bar magnet is shown. Irrespective of the shape, that is rectangular, hexagonal, irregular, or you can choose oval shape, and location of the chosen surface placed in the field where the magnetic field will exist. All the field lines entering the closed volume are offset by the equal number of fields line leaving this volume. This figure shows that magnetic field lines always form a complete loops. The closed magnetic field lines will tell about the zero divergence within the closed surface. That means there are no any positive divergence or negative divergence we have isolatedly. We always have a zero magnetic flux through any closed surface because isolated pole never exists. It always exists in the pair form. Now we will see the Gauss law of magnetostatics in the differential form. The continuous nature of magnetic field lines makes the differential form of Gauss law for magnetic fields more simpler, and in the differential form it can be written as del dot B is equal to 0. Here The left side of this equation is a mathematical description of the divergence of the magnetic fields, while the right side is simply 0. This means the divergence of the magnetic field at any point is 0, since it is not possible to isolate magnetic poles, that is north and south poles, separately. Means you cannot have a north pole without a south pole or vice versa. So the magnetic charge density must be 0 everywhere. That the divergence of magnetic field must be 0. To understand the meaning of each symbol in the Gauss law of magnetostatics in the differential form, you can look at this figure. The del is the operator and it is the vector quantity, so vector del is written. And dot is the basically divergence of vector field B. And B is the magnetic field defined in Tesla and it is the vector quantity, so represented with the arrowhead. And this is equal to 0. Vector fields with the 0 divergence are called as solenoidal. And all the magnetic fields are solenoidal in the nature. Thank you for watching this video.